In the second part of Chapter 8, we're going to discuss the stereochemistry associated with each one of these different types of mechanisms, the SN1 versus the SN2, and the E1 versus the E2. So first, let's start off with the SN1 mechanism. And what we're going to see is that it is always going to produce a mixture of the R and S compounds if a stereocenter is created during the reaction. Which means for us, remember, a stereocenter is going to be that carbon atom that has 4 different attachments associated with it. So if we generate one in the product of our SN1 reaction, we will generate a mixture of both the R isomer and the S isomer. One of the things that is going to discuss the amounts of those mixtures is going to be the type of environment that we are dealing with. So if we have an achiral environment, we will end up creating equal mixtures of the R and the S isomers. So we would have that racemic mixture that we talked about previous with equal amounts of the R and S. If we have a chiral environment, then we're going to create unequal mixtures of the R and the S isomer. One of them will be favored. So this is where we would see in our mixture that we would have an antiomeric excess of one of the isomers over the other one. So let's look at the conditions and kind of how we're going to get the mixtures of isomers that we're talking about. So first I'm going to look at that achiral environment. And remember, in the achiral environment, we're going to produce equal mixtures of our R and our S stereoisomers. So just looking at an example of our SN1 type mechanism, so we have our stereocenter to start with. So we have our chlorine coming out, we have a methyl group going back behind. And in our SN1 mechanism, the first step of this mechanism is that that leaving group, the halide, is just going to leave. So that leaves us with our intermediate, and that intermediate is going to be a carbocation. So what we'll need to recognize is with that change, the carbon atom that was attached to the chlorine in our initial reactant was sp3 hybridized. It had 4 attachments associated with it, so it had that tetrahedral nature. Once that leaving group is left and we have generated the carbocation, that carbocation is now trigonal planar because it only has 3 attachments to it. And then it has the vacant orbital for the positive charge. So this is a trigonal planar structure, which means when a nucleophile comes in, the nucleophile is coming in and attacking something that is very planar, which means it can attack from the front of it or it can attack from the back of it. So I'm going to bring in a new nucleophile, and I'm just going to use iodine as our new nucleophile that is going to come in and do the attacking for us. So this iodine can come in, if you think about it coming in from the back side of this very planar carbon atom, is what we're going to be looking at first. And if it comes in from the back side, that means the iodine is going to be pointing back for us, and that would push that methyl group forward for us. So that is one of the attacks that we can see happen. If we look at it from the other direction, since it is planar, that iodine can also come in and attack from the front face of that planar molecule. And if it comes in and attacks from the front of the molecule, now that iodine is going to be pointing out, which is going to push that methyl group going back. So when we actually look at the products, we have a new stereocenter, but you'll notice that those 2 isomers are different from each other. They are mirror images of each other. They're enantiomers of each other. We have created both the R and the S stereochemistry. So if we go through and we actually assign names for us, the top molecule with the iodine pointing back would be S3-iodo, 3-methyl, hexane, where the bottom structure, if the iodine came in from the front, would be R, 3-iodo, 3-methyl, hexane. So you'll notice in this very achiral environment, which is most environments, there's nothing else outside of the molecule that is predicting stereochemistry. We get that planar intermediate, And because that intermediate is planar, the new nucleophile can come in from either side of it. It can attack from the back, it can attack from the front, and in doing so, it generates the mixture of the R and the S isomers in our final product. So this would be a racemic mixture. We would have equal amounts of both of these because nothing is really dictating one over the other. So now let's look at what happens in a chiral environment. And the way that I'm going to generate a chiral environment is we're going to still start with the chlorine and the methyl group on carbon atom number 3. But now on carbon atom number 4, I'm going to make that a stereocenter as well. And I'm going to put an alcohol that is pointing out at you. So now I've put some more chirality into our structure. I put another stereocenter. And what we're going to see is that now generates a chiral environment that we're going to be looking at. Because in my mechanism, we're still looking at that SN1 mechanism, that chlorine atom is initially just going to leave. And it's going to leave behind that nice planar carbocation. But now adjacent to that planar carbocation, we have a hydroxide unit sticking out. So now if we actually look at our new nucleophile, which we said was going to be our iodine, coming in, it doesn't have as easy of a route if it goes to the front or if it goes to the back. So if we actually look at this, and we have the iodine coming in from the back like we did before, to that planar sp2 hybridized carbon atom, there's nothing really blocking it in the back. We have a hydrogen back there, but we also had a hydrogen in the previous one. There's nothing really blocking that attack. So if it comes in from the back side, that OH unit will still be pointing out. Iodine will be pointing back, which would have forced that methyl group to come forward. But looking at this molecule, now if it tries to come around and attack from the front, that front is somewhat blocked by that hydroxide unit. You can kind of think about it, it's there in front, it's got this steric bulk that we have now put in the front of that planar sp2 hybridized carbon atom, and it's going to interfere with the iodide ion coming in because now we have this bulky group sticking out in front. So the iodine will still be able to come in from the front, but not nearly to the extent as what it would have if that alcohol unit was not there. So we would still see a little bit of this being formed, but we would no longer see racemic mixtures. We would favor the back more so than the front attack because the back side is not blocked by anything, where that front side has a little bit of steric interference because of that hydroxyl group that is out front. So if we get ready to name both of these, the front one would be our 3R. We would also have 4S. 4-iodo, 4-methyl, and then hexanol. And that was 4S. With the other one, we would still name it the one stereocenter, the hexanol stereocenter. It's still going to stay the same. So this would end up being 3R and then 4R. 4-iodo, 3-methyl, hexane, 3-ol. So the one stereocenter does not change. That one with the alcohol unit, we have not reacted there. It has not changed, but we will see a change where the nucleophile still comes in and attacks, but this time we're no longer going to have a racemic mixture. We have generated somewhat of a chiral environment because we have put more chirality onto the molecule, and that's going to interfere with one of the stereocenters. So we will favor one over the other. So we would have an enantiomeric excess of the 3R4S, and we would not have as much of the 3R4R compound in solution. So we can generate non-racemic mixtures fairly easily. This is one of the ways that we can do so, having other chiral centers there. Another thing that does impact this is things like the inductive effect can impact it, so that we can have electron density on one side of the molecule that again would hinder something like a nucleophile coming in because of the electron interference. That electrostatic repelling factor can also impact this chiral environment. And one of the other things that you want to be looking at as well is that chloride ion, it is still there, and we have generated a cation, we have generated the chloride ion, and there's still an attraction there, so they're not completely separated from each other as well. So the front side will still be a little bit blocked by that chloride ion at the same time because it is still there. We kind of refer to this as being an ion pair attraction, because the chloride ion is still attracted to that positive cation that we just generated. It's still going to kind of block that front face a little bit because that's where it came off. It came off in the front. It's going to block that front face a little bit from the iodide getting in, because we will still see an attraction between the positive and the negative charge. So more often we do not produce purely racemic mixtures under most of our SN1 reactions. We typically do favor one over the other, even if it is just a slight favoring due to that ion attraction. So next, let's look at our SN2 mechanism. So remember, SN2 is our nucleophilic substitution, but this is bimolecular, which means both the nucleophile and the substrate react together at once. And what we're going to see with this mechanism is it only is going to produce one stereoisomer. So we refer to this as being a stereospecific reaction. We're not going to see mixtures of the stereoisomers. We will only produce one very specific stereoisomer. What we're going to see with the stereoisomer that we produce, it is going to be the opposite of whatever the original stereoisomer was. We refer to this as the backside attack. So if we look at our tetrahedral carbon atom, and I'm going to draw it a little bit different. I'm going to look at it specifically in that tetrahedral nature. So we've got the methyl group, we've got the long carbon chain, we've got the chlorine coming off carbon atom 2, we've got the hydrogen. What I wanted to note is I put that leaving group in the plane and I put it on a very specific side. So we're looking at it a little bit differently than what we would normally draw our structures, because I want to point out what we mean by this backside attack. So in our SN2 mechanism, the leaving group is going to leave at the same time that the new nucleophile comes in. It happens in one mechanistic step. So what we mean by the backside attack is that the nucleophile is going to come into that sp2 hybridized carbon atom, or sp3 hybridized carbon atom, on the opposite side of the leaving group that is leaving. So that's referred to as a backside attack. The nucleophile comes in the back door and the leaving group leaves out the front door. So we see this reversal in our stereochemistry because of the way the attack has to happen. You can't have both of them coming off and going on the same face. So if you try to have someone come in the front door at the same time someone's trying to leave out the front door, they collide. You can't have two people go in and out one door at the same time. So in our SN2 mechanism with this backside attack, the nucleophile comes in the back, the leaving group leaves out the front, and it happens all at once in one step. So that means when we look at our final product, we see a reversal in the stereochemistry that we would be looking at. We started off with an R stereocenter, and we would end up with the S stereocenter. And we will always see this relationship anytime we have an SN2 mechanism, since the leaving group and the nucleophile all have to interact with that carbon at the same time. One of the other things that we can look at is we can look at the intermediate. We'll look at the intermediate because we don't have we'll look at the transition state because we don't have an intermediate in this reaction. So remember, the transition state is where we have those partial bonds, bonds being broken, bonds being formed at the same time. So these are all three of the bonds on that carbon atom that are not going to change. We have the methyl group, we have the ethyl group, and we have the hydrogen on it as well. So then what happens in our transition state is we start to form a bond with iodine at the same time that the bond with our chlorine is breaking, is leaving. So this becomes our our transition state, where we have those partial bonds. And since we have to form and break all at the same time in that transition state, we can't have both the iodine and the chlorine on the same side. There would be too much steric bulk there. They would interfere with each other too much. So one has to come in on one side of the molecule, and one is going to leave from the other side of the molecule. So we see this somewhat planar transition state with bonds being broken and bonds being formed all at the same time, which is what leads us to the reversal of stereochemistry, a very stereospecific reaction. If we start with the R, we will only get the S product. If we start with the S reactant, we will only get the R product under these SN2 mechanisms. So now let's look at our E1 mechanism. With our E1 mechanism, remember this is elimination that is unimolecular, which means that the substrate with the leaving group is going to react to produce an intermediate, and then that intermediate will react with the base to get to the final alkene product. So it's a multi-step mechanism with a unimolecular rate determining step. And what we're going to see with the E1 mechanism is, once again, we're going to get a mixture of isomers. We will get a mixture of both the E and the Z isomers. We will typically not get 50-50 mixtures of the two isomers. We are typically going to favor the isomer with less steric strain. So we're going to favor the isomer that is going to have less steric strain for us. So remember, steric strain is where we try to put big bulky groups on similar sides or in similar spaces. So we're going to pick the one that has less steric strain. So let's look at an example of an elimination reaction. So I'm going to look at having my leaving group, and that leaving group is adjacent to a hydrogen. And remember, in our E1 mechanism, that leaving group is first just going to leave. So remember, that leaves behind a carbocation that is nicely planar for us. So this first step of the mechanism is going to be very similar to the SN1 mechanism that we looked at, where we get this carbocation intermediate. From here, what's going to happen is we're going to bring in a base, and I'm just going to use ethanol as my base. And remember, that base is going to deprotonate on an adjacent carbon atom. We do want to produce stable alkenes, so we are going to be very specific with the hydrogens that we will remove. So remember, the more substituted an alkene, the more stable the alkene. So I'm going to remove one of the hydrogens from the CH2 unit instead of removing hydrogens from the CH3 unit. So remember, alkene stability, and our goal is still to produce the most stable alkene. So from here, because we have free rotation around that double bond, I can initially have this same structure with the planar structure. I can pull off one of these hydrogens, which will go to produce the alkene. And if you'll notice, the phenyl group and the methyl group are on the same side. So when I get ready to look at my alkene, the phenyl group and that methyl group will also be on the same side. They started on the same side because of the way we drew our zigzag, and because that carbocation is planar, we initially have that phenyl group and that methyl group on the same side, and then I would also have my protonated ethanol as my other byproduct. But one of the things that we have to remember here, and how we're going to get to the other isomer, is that we have freedom of rotation around that single bond. So all I'm going to do is I'm just going to see rotation around that bond. So instead of having the methyl group be on the same side as the phenyl group, it's actually going to be on the opposite side of the phenyl group. So remember, that bond is constantly rotating, constantly rotating. Having them be in that orientation is one of the less stable. That's going to be looking at more of an eclipsed interaction between the phenyl group and the methyl group. So if I rotate into a more stable form, now we're looking at more of an anti-relationship between the phenyl group and the methyl group through that freedom of rotation. So this was really looking at those Newman projections. So because of that freedom of rotation, I can then take my alcohol and deprotonate this conformer, this rotated form. But now when I look at the double bond, that phenyl group and the methyl group are on opposite sides of each other. So in the first one, we have what we would refer to as our Z relationship. The two priority groups are on the same side. The bottom one, we would have an E relationship. The two large groups are on opposite sides of each other. And then we still have our protonated alcohol as well. So now we're going to talk about which one is going to be more favored. We have produced both of our products through freedom of rotation. Now we have to talk about which one is going to be more favored based on steric strain. And what we're going to see is that the E becomes our major product, our favored product, because of the steric strain. We have the two large groups on opposite sides, so that will be less strain for us. So it will be our major product. The Z conformation up here would be our minor product. We have those two large groups, the phenyl and the methyl, on the same side of the double bond. Remember, everything is planar because we've got sp2 hybridized carbon atoms. So now we start to see some steric interference on that top side of the double bond itself. so it would become the minor product. We would still get both products, but again, we would not get equal mixtures. We would get more of the major product and less of the minor product. So now let's look at the E2 mechanism. So remember, this is bimolecular elimination. So both the base and the substrate are going to react together to get to that alkene. And we have a very specific orientation that we need. We need the leaving group and the hydrogen atom to be anti-periplanar to each other. Because they have to have that very specific anti-periplanar relationship, once again, this is going to be a very stereospecific reaction. The orientation that our molecule adopts to have that anti-periplanar relationship between the leaving group and the hydrogen atom is what is going to dictate for us the E and the Z relationship. So what we mean by this anti-periplanar relationship is I'm going to go into a Newman projection. And I'm going to look down the adjacent carbon atoms that we need the leaving group and the hydrogen to be on. And what we're going to see is that we need the leaving group and the hydrogen that is going to be pulled off by the base to have this anti-periplanar relationship, meaning they have to be anti to each other and they still need to be in the same plane as each other. So this Newman projection is what we need to describe the orientation our molecule needs to adopt in order to have the reaction happen. Because remember, in our mechanism, the base is going to come in and pull off the hydrogen at the same time the leaving group is leaving. And in order for that to happen, we have to have the spatial arrangement for it to happen all in one step. There has to be room for the base to come in and get to the hydrogen at the same time that leaving group is leaving. And if we try to do that with the leaving group and the hydrogen not having that anti-relationship, there's too much bulk. There's too much trying to go on in the same area with the base coming in and the leaving group leaving that it will not happen. This is kind of the same rationale that we saw with the backside attack in the SN2 mechanism. We have to have the spatial arrangement for two things to happen at once. For the base to come in and pull out the hydrogen and the leaving group to leave all in one step, we have to make sure that they have the space to do so. And the only way they can adopt and have enough space is to have this anti-periplanar relationship within the molecule. And if you'll notice, because of that relationship, that is going to dictate what's on the same side in our double bond that we will be forming. So you'll notice here that we have two groups that would be on the same side in our double bond, and then we have two groups that will be on the same side in our double bond, and that's what's going to dictate the E or the Z isomer that we make, is where those groups are in this anti-periplanar relationship. If we have multi-anti-periplanar relationships, the major product is once again going to be the most stable product. So if we have multiple hydrogens on the front carbon atom, and it can adopt a variety of different anti-periplanar relationships, we're always going to go with the most stable product in terms of which anti-periplanar relationship we will adopt. So let's look at a couple of examples on how we're going to use this relationship to help us come up with the E and the Z orientation. So in our structure, we have a leaving group, we've got phenyl groups, we've got basically two stereocenters in our structure that we're going to have to account for as we get ready to look at our relationship. So in this relationship, just to give you the stereochemistry, we have a 1s and a 2r unit that we would be looking at. So this would be 1-bromo, 1,2-diphenyl, and then propane. So now what we have to look at is we have our leaving group, which is the bromine group, and we also have our hydrogen on the adjacent carbon atom. If I draw it in, that hydrogen is going to be pointing out of the screen. So right now in this orientation that we have, we do not have the anti-periplanar relationship. The bromine is pointing out of the screen. The hydrogen that needs to leave is also pointing out of the screen. So through freedom of rotation around that single bond, so think Newman projections, we are going to rotate our molecule so that it adopts the anti-periplanar relationship, which is going to have the hydrogen pointing up and the bromine pointing down and both being in the same plane. Because of that rotation, I have to then rotate all the rest of my molecule parts in order to maintain the same stereocenter. So I need to make sure that I am maintaining that 1s 2r relationship as we go through this process. But what I am looking for in order to do the reaction is the hydrogen and the leaving group need to have this anti-periplanar relationship. So one pointing up and one pointing down. So now that we have adopted that relationship, I can bring in my base, and I'm just going to use hydroxide as my base. It's going to come in to deprotonate that proton. Those electrons are going to come down to form the double bond, and the bromine is going to leave. Because all of that happens in one step, we have already dictated what is going to be on the same side of our alkene. So the phenyl group is pointing back, and the hydrogen is pointing back. So they will be on the same side. The methyl group is pointing forward, and the phenyl group is pointing forward. So they would also be on the same side of our process as well. So it's the anti-periplanar relationship that is dictating the stereochemistry that we're looking at around our double bond. I would have then also in this mechanism produced water, and we would have the bromide ion as well. So if we look at naming this relationship, this product has E stereochemistry, so it would be E1,2 diphenyl propene. And that would be the only product that we would end up making because of the anti-periplanar relationship. So let's look at another example. The only thing that I'm going to do is I'm going to take this molecule and I'm going to switch one of our stereocenters. So this time, instead of having the bromine point out, I'm going to have the bromine point back. So the relationship here is now 1R 2R. And the rest of the name would stay the same for us. So the only thing I've done is I have changed one of the stereocenters. We have made it 1R 2R instead of 1S 2S. But I still have to do the same rotation. So you'll notice, sorry, the phenyl group should be pointing back there to keep it the same. So the phenyl group is still pointing back. The hydrogen is still pointing forward. So we're maintaining that same stereochemistry. The only one I wanted to change was the bromine. The bromine is now pointing back as well. So with this relationship, I still have to have the anti-periplanar relationship between the hydrogen and the bromine in order for the E2 mechanism to occur. So what that means is that hydrogen that was pointing out, I now have to put it in the plane. I then have to make sure that I am rotating everything else appropriately to maintain that R stereocenter. The bromine that was pointing back now has to be pointing in the plane. And again, then I have to rotate everything else to make sure that I am once again still maintaining that R stereochemistry. So now my base can still come in just like it did in the previous. Pull off the proton, those electrons go in to produce our double bond. At the same time, the leaving group, the bromide ion, leaves. But what you'll want to notice this time is the relationship between those two phenyl groups. Because of the new orientation in the anti-periplanar relationship, both phenyl groups are pointing back, so that means both phenyl groups will be on the same side of our double bond. The methyl group and the hydrogen are then pointing forward, so the methyl group and the hydrogen are then on the same side as well. So now the relationship in my final product is going to be the Z isomer. The two phenyl groups are now on the same side. So I would have the Z 1,2 diphenyl propene. So in these E2 mechanisms, the stereochemistry that we start with is what is going to dictate for us the stereochemistry around the double bond that we end up with. And we will only end up with one product because we need to have that anti-periplanar relationship between the hydrogen that our base is pulling off and the leaving group that is on the adjacent carbon atom. So this is where Newman projections will really start to help you. If you can go in and draw some Newman projections and look at that freedom of rotation once again, that's how you're going to be dictating whether you have an E stereocenter or you have a Z stereocenter.